Welcome back. We're going to continue our discussion on week 2 material. Now, I left all of you with 4 different elements and have you write the electronic configuration. Because these elements require a ton of time and explanation, I decided to not continue in that video but decide to do it as a fresh video. So here's the orbital sequence. I could have used the periodic table, but it makes more sense to use this for explaining these. Now, titanium is a little tricky, so I'm going to do that last. But let's start with mercury. Okay, if you notice, mercury is my element right here, and if you notice, the 4F is squeezed in between the 6s and the 5D. Now, keep in mind, if they had included it here, then we would never have that problem. But I've already pointed that out. The D's are one short of the row that it's supposed to be in. Okay, so that's why we have 5D instead of 6D, because if this were to be matched, then we should be in 6D. But no, that's a inherent problem, but that's the way it's supposed to be. Okay, so we have a 4F sitting in between our 6S and 5D, right? So what I'm going to do is I'm going to start off with the correct configuration, because keep in mind, I did not I was not teaching the concept. I left you all with a question, so it would have been 80 protons and 80 electrons, right? So I'm going to write the corrected sequence first and then explain to you what you should have had and what are the things you should have flipped. Okay, all right, so let me get a different color. It seems like too much red here on the screen right now. So 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, and 6s. Now start filling in the electrons. So 2, 2, 6, 2, 6, 10, 2, 6, 10, 14, 2, 6, and 10. Now if you add all this, it would end up somewhere near 78. Okay, this would all add up to 78, and you would need 2 electrons to get to 80. Okay, 80 electrons, so we will have 2 here. Now if you pay attention to this 2 and the Roman numeral, of course this particular image doesn't have it, but if you actually go to look at the periodic table, it will read 2b. That means it has 2 electrons. Okay, now transition metals have variable oxidation state. I think I've mentioned this earlier, but I'm going to mention it one more time, which is why we use Roman numerals as we'll start to name these compounds in the future videos. Variable oxidation state. That means they don't have a fixed number. That means I'll explain that here. So we have a 2b, right? So mercury can technically lose all 2 of its valence electrons, be Hg2 plus, or it can only lose 1 and remain as 1 plus. Okay, this is a transition metal, so they can have multiple oxidation states depending on what it is getting paired with. Okay, so now that's the correct sequence. Let's go ahead and write what you should have had. Okay, now I guess it's easy to just do the corrected sequence in the first place if you're getting comfortable, but if you're still struggling, hey, it's not the end of the world. 2p, 3s, 3p, 3d, 4s, 4p, 4 well, actually let me stop here for a second, and because I'm starting to write the correct sequence again, because I don't want to do that again, because I clearly said I will be doing a difference here. So 3s, 3p, right? And then let's get rid of this as well. Okay, so it should have been technically 4s, 3d, okay, and then 4p, 5s, 40, 45p, 6s, 4f, and 5d. This is what, if you had simply followed the sequence, this is exactly what you should have had. Okay. Now, I don't recommend you fill it because there's no point in doing it. However, if you want to fill it and then switch, that's fine, but then some people can still get it wrong. So here's what I want you to do for such a lengthy element that is wherever you see 3's and 4's and 5's are mixed up, put them in such a way that they are all together with their own family. So I'm going to move the 3D here. Let me get a different color, perhaps a blue. Okay, all right. So I'm going to move this 3D over to this. So the 4s comes here, and then I'm going to do the same here. The 4, okay, can move over here, and the 5 can move over back. You're doing multiple swaps. Remember, I said as the element becomes larger and larger, the amount of work that you also have to do would become larger and larger, right? So the 4f, however, this is going to be, it's not going to be a simple swap. The 4f will go right over here, okay, and then the 5d would have to go over here. Okay, every number must be with its the same number category, just a different orbital. Okay. Now that's how I ended up with what's on the top. Now I could do it without having to do what I did on the bottom, but some of you may not be able to do exactly that. All right, moving on. Let's go to the second element, which is tin. I'm going to bring the sequence back. So, all right, so we got tin, which is right over here. Again, this is not as much of an issue because we don't have the 4f staring at our face. So we have our tin, which is got 50 electrons. So which means we have 50 protons and 50 electrons, right? So I'm going to only write the corrected sequence here, and I've already explained it kind of why I did what I did in the previous element. You just have to keep switching until you pair the right element. So 1s, 2s, 2p, 3s, 3p, and I believe we're going up to 5th row, so we're going to have to include 3d, 4s, and then 4p, 4d, and 5s. And of course, tin is in the p band, so 5p also joins the party. All right, so now let's go ahead and fill everybody with electrons. So it would have to be, let me give it a different color so I can make that difference. So 2, 2, 6, 2, 6, 10, 2, 6, 10, 2, and well, if you add all this, I know what this number is, but if you just add all this, it'll be 10, 20, 10, and then you got 20, 28, 30, 36, and 46, 48, and we need 50, so we will need 2. So we needed 48 plus 2 would give you 50 electrons, right? Well, that makes sense because now I've told you that if the last orbital is 5p, but if there's one more with the same number but a different orbital, they both are together valence orbitals. I have pointed that out because if you go back to your original periodic table, you will see that this is actually 4a. It's in the column of 4a. That means it is tin. Tin can lose up to 4 electrons. Now tin is technically not a transition metal, but it is not an alkali or alkaline earth metal either. So it can have variable oxidation state. I know for a fact tin can lose all 4, or it can only lose the plus 2. So at least you will have more than one. So when you do write your names in the future, which I will discuss, you will include Roman numerals. Don't worry about it now, but I'm just pointing that out to you, that it is not a alkaline or alkaline earth metal. It's also not a transition metal, nor a F block element, but it's on its own category. All right, so that is tin for you folks. Now if you want, maybe at a later time, you can just email me and I will write you the incorrect sequence, but you should just be doing exactly what I did in the earlier one. All right, moving on. So next element on our list is bismuth, which is also right over here. Okay, and it's also in the same row as mercury, so we're going to do pretty much everything we did for mercury. We're also going to do it for bismuth, and bismuth I believe is 83. Okay, so just start shooting orbitals: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d. Believe I got that, and I got 6s and 6p. Okay. All right, if you start shooting electrons into it, let's get a different color, perhaps maybe a blue. These are the only colors that I find really like sparking at your face. So 2, 2, 6, 2, 6, 10, 2, 6, 10, 14, 2, 6, 10, 2, and well, if you want to challenge me and say this is a different number, then it will have to be 3. I mean, because if you look at the periodic table, this whole sequence right here is the valence electrons. Remember, it's not just the p. Okay, if it's got another orbital with the same letter, then they both together are valence electrons, or valence orbitals with valence electrons. So bismuth can technically lose all 5 and have +5, or it can lose 3, be +3, or it can lose just 2 out of the 5, be +2. This is what we mean by variable oxidation state. Because it can have a variable oxidation state, it must be considered when you name. In the nearby videos, we will include Roman numerals. Okay, keep that in mind. It's not an alkaline metal, it's not an alkaline earth metal, it's not a transition metal either, but it's on its own kind. So keep in mind that. All right, it is a metal. Okay, it is a metal. Anyways, that's bismuth. Let's go to titanium. Remember I said titanium and actually the couple of elements around those all have that same problem. It's not with the configuration itself, it's just how you determine the valence orbitals. All right, let's find titanium. It's right over here, so we don't have too many to worry about. So what's the formula for the atomic number for titanium is 22, so it has 22 protons and 22 electrons. So 1s, 2s, 2p, 3s, 3p, 3d, and 4s. This is the corrected sequence. I am not writing the incorrect sequence anymore. Okay, just the corrected sequence. So if you start filling electrons, you would end up with this as probably your configuration. Okay, now this is not as easy. If you look at the periodic table, the number for this is 4b, I believe. Titanium is under 4b. What that means is it can lose up to 4 or anything less than 4. Okay, now the valence orbital is not necessarily just the 4s. It would have to be both of these, because there's no way 4s2, remember that number indicates the number of valence electrons. If it is 4, well, 4s cannot be the valence because that only accounts for 2, but we need 4. So this is the valence orbital. This is a weird combination that you may not ever like to think that how does that even happen. So this is the valence orbitals, and we have 4 valence electrons. So titanium can lose all 4, or it can lose just 3, or it can, let's just do, keep in mind when it loses in chemistry we call positive charge, and when we gain we get negative charge. Again, this is a transition metal. Okay, so it's got variable oxidation state. All right, so there you have it, folks. These are the transition metal compounds and how you write electronic configurations for them. I have walked through 4 different examples, and if you feel you've got it right, practice a few more on your own. Okay, see if you get it right, because when you finish you can go to Wikipedia and type in, say you're doing for molybdenum MO42. You write the electronic configuration and Wikipedia will give you the configuration, or somebody else out there may have done it for you. Alright, so that's video 5 of week 2. Alright, doing electronic configuration for transition metals. Stay tuned for more videos.